Okay, this is simplifying radicals and radical expressions. Learning objectives for today is to evaluate different degree roots, simplifying, multiplying, and dividing radical expressions by using radical properties. So here are your standards. Okay, so corresponding to every power, there is a root. For example, remember your perfect squares. You have 3 squared is equal to 9. You would say that the perfect square root of 9 is 3. So on and so forth. For all of these, they have perfect cubes. For example, 3 cubed. The perfect cube of 27 would be 3, because 3, you're looking for groups of 3. Here, you're looking for groups of 4, and groups of 5, so on and so forth. So we say it increases. We have square roots, cube roots, fourth roots, fifth roots, so on and so forth, and forever. So the thing that you need to know, we've done square roots up to this point. But now, the square root, the index here is 2. The index is the degree of the root. In this case, we're going to have other numbers that are going to be for your index. So you need to know that if it says 2 here, that means square root. Or if it doesn't indicate it, it means square root. If it says 3, that means cube root. If it says 4, fourth root, so on and so forth. And this here, the radicand, that's the number or numbers that are underneath the radical part. So I'm going to do side by side 2 different problems. So if you notice from the previous slide, I told you that if there is no index here, you automatically assume that it's 2. Okay, in previous lessons, remember when you did this, you did 16 and 3. This was your perfect square root, and it comes out, square root of 16 is 4. And then you have your square root, your index. You don't have to put a 2. I just did that just for practice sake. You have your 3 that does not have a pair. If you want to also think of it in terms of the jail set, you have your pair of 4s. 1 makes a break for it. You have a 4 on the outside, and then you do the exact same thing here. X to the third, divide that by 2. You get x to the first with a remainder of x. So that means 1x comes out, 1x stays underneath, and there is your final answer. How this changes, instead of looking for pairs here, we're now going to be looking for groups of 3. So I'm going to have to break this 48 down into different pair set. You can still break it down into 16 and 4. That's fine, but I'm going to break it down into 8 and 6. I'm going to do this a couple different ways. The reason I broke it down into 8 is because if you know your perfect cubes, the perfect cube of 8 is 2 to the third. So that means that this is going to be a set of 2. So 2 times 2 times 2 gives you 8. And then you have your 3 times 2. You're always looking for a group that's pertaining to the index. So we're now looking for groups of 3. Okay, so group of 3, we found group of 3 2s. That means 1 2 is going to come out. Remember, in the jailbreak, only one of them actually makes it. This 3 and 2 set here, that stays underneath because it does not have a group of 3 to get to leave with. So that means we say 6 or 3 times 2. You do the index the exact same way. So I'm going to do the x to the third. Instead of dividing it when you had an index of 2 over here, we divided by 2. Here, since we have an index of 3, we are dividing this by 3. So we get x to the 3 divided by 3, which is 1. That means we have a group of 3 x's, which means 1 comes out. If you had a remainder set, that would go underneath, but we do not in this case. So this is our final answer. So this is basically what we're getting into, and you might have to watch this video a few times because this can be a little tricky. So, okay. So just to kind of remind you, cube root is the same as a third root, cube and third, and 3 is odd, so there's only one real cube root of a number. Negative 10 is the only real cube root of negative 1,000, because again, you have a group of negatives. You will still have a group. Negative times a negative times a negative still gives you a negative. So anytime you see, there's going to be a couple rules that are associated with this a little later on, and I'll show you that in a sec, but we're going to get some practice with the positives. Okay, so I told you, you always look for the index. and in this case the index is 3, so that means we are looking for a group of 3. We're going to break 375 down. And if you know your perfect cubes, that's going to be the important set here. Like I said, perfect cube of 8 is 2 to the third. Perfect cube of 27 is 3 to the third, so on and so forth. Perfect cube of 64 is 4 to the third. Perfect cube of 125 is 5 to the third. So we say we're trying to look for groups of 3 here. So what I notice is that this can be multiplied. 125 and 5 is what 375 can be broken down into. I can actually stop right here because I know that 125 is a perfect cube. That means it's multiplied 5 times 5 times 5, so it has that group of 3 5s, so that means 1 is going to come out. And this 5 here, this is a common mistake that people do when they have this. They kind of forget the ones that are up here. This 5 here does not have a group of 3 to leave or get out of the jail, so we say that he stays underneath the jail. So the one that comes out is the 5. You have a cube root of 5 as well, and there is your final answer. So again, when you see the index, you're always looking for maybe some shortcuts. The group of 3s, cube roots and square roots are kind of the tricks. When you get up into the 4th and 5th roots, those can be a little more tricky, but again, it's all knowing your multiplication tables. Okay, so let's go to the next one. Here, like I said, exact same thing. If you want to do it the long way, that's completely fine. For example, if I broke this down, this would be 5 and 243. Have some sort of way to remember, because when you get a little bit more in terms of numerical values, you don't want to forget these prime numbers that are in the higher levels of the factor trees. So I have 81 and 3. There's another one. 81 breaks down into 9 and 9, and then 3 and 3, and then 3 and 3. Okay, so those are my perfect breakdown of 12, 15. We have an index of 5, so we're looking for groups of 5. So what I'm going to do is I'm going to write this just in expanded form, just to kind of show you, because again, this is an index we have not done before. But I have a 5, cross it out. I have a 3, cross it out. I have 1, 2, 3, 4 threes, so I'm going to do 1, 2, 3, 4 threes. And since I'm looking for that index of 5, I'm looking for a group of 5. Well, I see a group of 5 threes right here. So you have 5. So again, it's the same concept. If you have 5 that are underneath the radicand, that means automatically that 1 comes out. You have that index. And then you have the 5, this 5, which does not have a group of 3s to leave the jail, so he stays underneath. And there's your final answer. Okay, this is when we're going to get into a few of the rules when it comes to different number indexes or indices. Namely, when there's a negative radicand, we're mainly going to deal with negatives in the odd roots. We're not going to be dealing with them in the even roots. The reason is because it gets a little more complicated when you get above an index of 2. So if you have an even root, namely the only even root you're going to deal with is the square root, or with an index of 2, that's going to involve your imaginary number. When we come to odd roots, when I say odd, I mean 3 radicand, or index, I should say, 5 index, or above, anything that is an odd number root. What's going to happen is if you have a negative number, a negative 1 is going to actually be able to pop out, is going to be able to leave the radical. Again, even roots, the only one you're going to deal with in Algebra 2 is the one that has an index of 2. So jumping right into this. Again, you identify what your index is. So we have, this one is odd. If you look at your notes, if you have an odd index, what automatically pops out? Well, you bring out a negative 1. So odd pops out, or odd index, if it's negative, that means the negative number 1 pops out, and then you deal with everything like you would on a normal cube root basis. So 256, one of the things that you're going to want to start getting a little bit quicker at is knowing if you have cube root versus fourth root versus square root, what your cube roots are, what your fourth roots are. That's part of multiplication. What I recognize is that I have 64 times 4 gives me 256, and this 64 is the same thing as 4 cubed. So that is a cube root. So what pops out here is going to be a 4. So you have a -1, you have a 4. This 4 here does not have a group that he leaves with. Sorry, that's a 3. So that means he remains, and then now I'm done with the numbers. So I can kind of cross those out if you want to. And then you do the exact same trick with the y to the 7th, the variables. So you divide it by the index. So the index here is 3, so I'm going to divide by 3. So y to the 7th divided by 3 from middle school or from elementary school, that equals y. 3 goes into 7 2 times, so there's a remainder of 1y. So that means this guy here is going to be outside of the radicand. So that's y squared, outside of the radical. And then you have the y to the first, which doesn't have a group set of 3, so he remains on the inside. Then you have to simplify this. So I have -1 and 4 become -4. You have the y squared, and then we have the cube root. Let's write that a little neater. Cube root of 4, and don't forget this y here, and you are done. That is your final answer. Okay, so this is a even root. So what you're going to do, you have a 4, so that means you're going to try and break it down into pairs or groups of 4. So what I know is I have 12 and 12 multiplied to give you 144. I have 3 and 4. I have 2 and 2. I have 3 and 4. I have 2 and 2. And again, if it's one of those ones that you need to keep track of the numbers that are the prime numbers, you can always highlight them, circle them, whatever it is you want to do. What I see, my group of 4 that I have is 4 2s. So if I have 4 2s, that means 1 is going to actually pop out of the radical, underneath the radical. So that means I have a 2, and I have my fourth root or index. And now I'm going to deal with the numbers so that are left, which is a 3 and a 3, which multiplies to give you 9. They do not have a group of 4, so that means they have to stay underneath the radical. So now I'm going to deal with my other numbers, which are the variables, other parts. And remember what I do here. I take x to the 8th, and I divide it by the number, the index number, and I see how many times it goes in. In this case, 8 divided by 4 gives you 2. So that means you have an x squared that's going to pop out of the radical. And I do the exact same thing with the y. In this case, the y value is y to the 13th, and you divide that. And remember, you're going to have a remainder here because it's not completely divisible by 4 in a nice way. So we have y to the 4 goes into 13 3 times. Your remainder is y to the first. So what that means is that you're going to have 3 y's that are going to be outside the radical, and that remainder one, y to the first, if you want to put a 1 there, is going to remain underneath the radical. And there is your final simplified answer. Okay, this next one, again, if you want to pause the video and try this one on your own, that's fine. We have an index of 3, so it's odd. So that means, since it's odd, that means a -1 pops out. And so we have the -1 cube root of 8, 64, x to the 4th, y to the 25. Now, I'm going to go through this one, like I said, same deal, breaking it down. So what I saw is I have an 8 and 108 and I'm looking for cube roots. I see that I have a cube root of 8, so I can stop with that one. 108 breaks down into 27 and 4, and I can stop with this one. You can pick different numbers and break them down into the smallest prime numbers, and that's fine. The problem is with that, you're going to have a lot of 2s and 3s all over the place, and keeping track of them is kind of a pain. So you want to be able to look for those perfect cubes. So what I say is okay, I have 8 here. That means a 2 is going to pop out because the cube root of 8 is 2. You don't believe me? You can plug this into your calculator. Do 8 to the power of 1 divided by 3. That will give you 2. Exactly like that with the parentheses and everything. So we have a negative 1. I'm going to put this over here because I'll have a little more room. We have a negative 1 times 2. So that means that 8 goes away, so I've already dealt with him. And then I have the exact same thing for 27. So 27's perfect cube is a 3, so that means a 3 comes out. I've dealt with him, so I can erase him now. And then I have my 4 that is still remaining. So I'm going to put my index of 3, and then I have my 4 that's still remaining. Now the thing that I need to make sure that I do is I need to do my variables. So I'm going to do my variables over here. So x to the 4th, it's a cube root, so I'm dividing it by 3. X, 3 goes into 4 once, and there is a remainder of 1x. So that means 1x comes out, 1x stays underneath the radical, and you do the exact same thing with y. So we have y to the 25, so we have y to the 25. Divide that by your index of 3. So y to the 8th, because 3 goes into 25 8 times, and there is a remainder of 1y left over. So 1y is going to be underneath the radical. And then your y to the 8th, y to the 8th is going to go outside of the radical. So now if you want to clean this up and simplify it, you do the negative 1 times 2 times 3, which gives you negative 6, x, y to the 8th. Then you have your index of 3, 4x, y. Nice, long, and ugly problem, but that is the end result. Okay, here are some other rules, some other properties that we have gone through with the square roots, but now this is the same thing for cubes, fourth roots, so on and so forth. It basically says that if you have the same index, you can consolidate them or put them together underneath one jail cell, if you want to think of it like that. Same deal here. If you have index on the top and the index on the bottom, you can consolidate it into one fractional index and simplify it from there. So we're going to do examples that are associated with this type of theory now. So next is going to be this. So I see, first and foremost, that I have two of the same indices, or indexes. So I rewrite it as one index. So after this, what's important is you need to make sure that you look for, again, we have an odd here. So odd means that automatically a negative 1 pops out because you have your negative here. So I'm going to rewrite this so I don't have to worry about the negative anymore. So we have 6 and 16. And then from here, you're going to break it down just like you did in previous examples. So we got 3 and 2. We have 8 and 2. Then I'm going to circle my prime numbers because this is going to get a little bit on the complicated side in terms of the amounts. We have 2 and 2. And then I look for groups of 5 because of my index. So I have my group of 5 here. So I have 1, 2, 3, 4, 5 2s, which means 1, 2 is going to be able to come out. So I have my -1, I'll just use that, times 2, and then I can cross these off as I go, and then I'm left with my 3 that's underneath is the radicand. So we have 3, and then once I've taken care of all that, I simplify it into -2 fifth root of 3, and then I'm done. Alright, same deal. So we have our index of 4, and like I said, I like to combine these, and 25, 50, consolidate is another word for them, and then we have x to the 3rd and x to the 6th become x to the 9th. So when I do this, like I said, I would not suggest multiplying 25 and 50 and then breaking it down. You already have it broken down in terms of parts here. And if you want to highlight your prime numbers as you go, that would be perfectly fine. You want to circle them, that's fine. Just make sure when you do this, you have some sort of way to remember what your prime numbers are, because a lot of the mistakes that I see are people that they forget a prime number that's like way up here. So like for example that 2. What I do see here is I have a group of 4 5s, which means one of the 5s is going to come out of the radical. And then I have the 4, and I left a little bit of space because I'm going to see what's what. I do know that I have this remaining 2 that goes underneath the radical. Radicand number is because it does not have a group of 4 to go with it. So now I'm done with the numbers. So now I'm going to deal with the variables. So I have my x to the 9th right off to the side, x to the 9, and I divide it by the index, which is 4. In this case, I get x squared because 9 divided by 4 gives you 2, and there is a remainder of 1x. So that means that remainder goes underneath the radical, and the x to the squared comes outside. And that is your fully simplified form. Okay, so if you want to try this one on your own, you can pause it, but I'm going to go ahead and actually do this. If you notice, we do not have an index here, so that's automatically assumed to be 2. If you want to put that, that's fine, so that means we're looking for groups of 2. So I'm going to do the numbers. We got 72 and 10. I'm going to add the exponents here, so there's an imaginary 1 on this guy here, so that means x to the 4th. Then we have y squared, y to the 3rd is y to the 5th. So if I break this down, like I said, I'm looking for pairs. So I got 36. That is a perfect square root times 2. And then I got 5 and 2. And then I have another pair in terms of the 2 as well. So what comes out is my perfect square of 36. A 6 comes out. And then I'm left with another thing that comes out as well, because I have 2 2's here. So that means 2 2's comes out. Only 1 comes out because you have a pair, so 1 comes out. And that's dealing with the numbers. We still have the 5. Don't forget the 5. And then we're basically done with that. Now let's deal with the variables. We have x to the 4th. I divide that by the index. I get x squared, so that x squared comes out. So, of course, I did not do this very well. So what I'm going to do is write it like that. And then we have x squared. And then I'm going to do the y's. So y to the 5th divided by 2 gives you y squared, because 5 divided by 2 gives you 2 with a remainder of a y. That means you have a remainder of a y under here and a y squared out here. And then you simplify the remaining parts. We got 12 x squared, y squared, square root of 5y. Now, if you wanted to, it's up to you, completely up to you. This would not be incorrect or more correct in any way, but if you wanted to put like a little imaginary 2 rather than just imagining the 2, that's fine as well. Okay, so this one, again, what you're looking for, don't let the index and the squared intimidate you. You literally want to break it down into smaller more manageable problems and the smaller, more manageable problems are you work from the inside out. So let's work this guy first before we square the whole thing. So I'm looking for a cube root, and 343 actually breaks down into 7 times 7 times 7, because 49 times 7 gives you 343, and then the 49 breaks down into 7 and 7. So I have my cubes, which is kind of nice. So what I do is I do this. Don't forget about the squared. A lot of people kind of forget about the squared. They kind of go too fast and forget about the squared. But here I look at and I see I have my group of sevens, 3 7s, so 1's going to come out, so that means the radical goes away completely, and I'm left with 7, but don't forget that squared, and 7 squared will give you 49. So anytime you see something like this, don't get intimidated by it. You work from the inside out and do the exponent last. Okay, same deal. So what I just said, work from the inside out, do the exponent last. So we're going to look at this. And if you know your perfect cubes, you know that 81 does have a perfect fourths. You know that 81 does have a perfect 4, but I'm just going to kind of show you as is. It breaks down into 9 and 9, 3 and 3, and 3 and 3. That is 4, a group of 4, because that's our index. So that means this entire thing in parentheses just simplifies to 3. Don't forget your 5. This 5, bring it down. Make sure you bring it down. And then we have 3 to the 5th. So 3 to the 5th is a nice whole number of 243, which is kind of nice. Okay, so one of the things you want to make sure of, and this is in your notes, you only need to rationalize square roots. You can leave all other roots with radicals in the denominator. So when you are doing this, just make sure your simplifying is accurate, because you mainly want to rationalize the denominator with square roots. So remember the rule. In this case, you're looking for fourth. Your index is 4, so you're looking for groups of 4. Well, 16 and 81, you want to simplify in terms of 16 and 81 first, if you can. These don't have anything nice that go into it, so what you can do is use that rule to say that you have the 4th root at the top and the 4th root at the bottom. So 16 actually has a perfect 4th root, because 16 is 2 times 2 times 2 times 2. That's your 4th root. And then we have the same thing for 81. Has a perfect 4th root. 3 times 3 times 3 times 3. So if that's the case, again, you're looking for fourths. For groups of 4, we have a group of 4 2s, we have a group of 4 3s. So this whole entire thing simplifies into 2/3. And that's it. Okay, at first glance, this definitely looks a little on the intimidating side. But again, if you use the rule, it's not too bad. It is a little on the tricky side, I will say. But the rule is, make sure you kind of consolidate and do 216. I'm going to do my algebraic trick in a little bit to simplify it. So we got 8, x to the 8th, y to the squared. This is why Algebra 1, knowing Algebra 1 is so important, and if you don't know Algebra 1, this can be very, very difficult, is because if you reduce this, for example, 216 can be reduced into 27. Okay, so 216 divided by 8, if you do that in a calculator, 8 goes into 21 twice, a remainder of 5, and then you have a 7 eighths left over. This is the main thing that I wanted to do. So x to the 6th, x to the 8th. Remember the whole subtraction. We have a subtraction of indices, 8 minus 6, because the 8 is on the bottom. That means you are left with an x squared on the bottom. The 5 and the 2 for y, that means you're left with a y to the 3rd, and then you have this entire index of 3. So now we're looking for groups of 3. So this, when you do this, you want to treat these as individual parts. For example, let's do the 21 or 27 first. The cube root of 27, 27 can break down into 3 times 3 times 3. Well, that's a group of 3's. So that means automatically a 3 pops out. So that's done. Let's do the y next. So the y is going to be y to the third. So y to the third, you divide that by your index, which gives you y. So that means a y pops out. Now the problem is that we have an x squared. But if you do x squared divided by 3, see how this number is bigger than this number? That means it has to stay the same. So this is going to simplify into 3y over cube root of x squared. And that's it. That doesn't look very nice, but it's a little bit easier to deal with than that. Okay, so same deal. Don't forget, because in this case we have an index of 2, so we're looking for perfect squares. This is already simplified for us. We can, we can simplify it, I should say. 48 divided by 3 gives you 16. The x to the third, x to the first gives you x squared on top. The y to the third stays on the bottom, and we have our index of 2. So the nice thing is that if you know your perfect square roots, square root of 16 is 4. So that one's done. Square root of x squared, if you want to kind of think of it like that, you can still do the radical part where you do x squared divided by 2 gives you x. It's the same deal. That guy goes away. And then we have our last, but certainly not least, is our y to the third. So our y to the third divided by 2 gives you a y, because 3 divided by 2 is 1. You have a remainder of another y. So we have a y that stays or comes out, and then we have another y that stays inside. Now this is where this is tricky. And the reason that it is tricky is because when you do this, since this is a square root, you have to rationalize the denominator. So it's an Algebra 1 thing, but again, welcome to Algebra 2. So I'm going to multiply the top and the bottom by square root of y, because that's going to rationalize the denominator. It's basically like multiplying the problem by 1. And when that happens, I get a 4x square root of y on top. This y and this y become y. So you basically get y times y, which gives you y squared. And that is it for that one. Okay, coming down the home stretch, now we have our word problems. So we have the base of a triangle is cube root of 16. So if I know what the base is, cube root of 16, this is from geometry. It's also from middle school as well. And then we have the height is the cube root of 6. So we're trying to find the area of the triangle. So area of a triangle is equal to 1/2 base times height. In this case, we have our base is cube root of 16. So we have cube root of 16, and then we have our height, which is the cube root of 6. Remember this part here, it can be consolidated into one cube root, and then we have 16 times 6. You break this down and look for those cube or groups of 3. So what I see is I have 2 and 8, and I'm going to stop there because that's a perfect cube, and I have a 2 and a 3. We don't have anything in terms of another group of 3, but this guy here is a perfect cube. So he's actually going to come out, perfect cube of 8 is 2. So we have 1/2 times 2, because that perfect cube comes out. And then we have the 2 and the 3 left underneath it's the radicand, so underneath the radical. So you have the 2, the 3, and the other 2 as well, which gives you 12. So when I simplify this, you're just left with the cube root of 12 as your area for this triangle. And last but certainly not least, you have volume, and if you remember volume, base times height times the thickness in the third dimension. So we have cube root of 42 times the cube root of 15 times the cube root of 36. My way of doing this is to consolidate this 42, 15, and 36 and look for those groups of 3. And what I basically did is I just kind of broke this down to 7, 3, and 2 because that's what 42 breaks down into. You have 3 and 5, and you have 2 and 3 and 2 and 3. And now you look for groups of 3. So I have 1, 2, 3 threes. I have 1, 2, 3 twos. But all the rest do not have a pair of 3s to kind of go along with. So we have 7, 5, and 3. So I'm going to be left with 6, and 7 times 5 times 3 gives you 105. And don't forget the index of 3 at the end, so you know that it is what you started with. And don't forget, one of the things I should have done is inches cubed, and in the previous one as well, it should have been centimeters squared. $40 minutes.